In the last lecture, I mentioned about the quantum Bochner theorem that certain positivity condition implies the existence of a state rho. This was first introduced in the PhD thesis of M.D. Srinivas. Sometime in the 60s, and there is a paper by Srinivas and Wolf, I think, and I understand, which contains it, and I understand Dr. Prabha Mandyam has a copy, but right now she doesn't have. Okay. So, let me summarize what I said in the last lecture. We introduced coherent vectors through exponential vectors, defined Weyl operators, and which constitute a projective unitary irreducible representation, and I defined the notion of the quantum Fourier transform. And there is one interesting formula which is quantum Fourier inversion formula, which is interesting in its own right. So, quantum Fourier inversion formula. So, if you have the state rho, correspondingly you have this rho hat of z. The problem is to recover rho from rho hat z. Now, if you consider Rn and then the Hilbert space L2 of Rn, and you consider the Hilbert-Schmidt operators here, they constitute a Hilbert space with the scalar product between any two Hilbert-Schmidt operators being equal to trace of A dagger B. Hilbert-Schmidt means trace A dagger A is finite. So, they form a Hilbert space with this scalar product. And this Hilbert space can be identified with also L2 of Rn tensor product L2 of Rn as follows. You first look at all operators of the following form: EU and then E, V, but you conjugate the entries of V. This is a rank 1 operator. Namely, if you apply to any vector psi, the image will be, you simply contract this and then that multiplied by u. That is this operator. This is a rank 1 operator, and you put this in correspondence. You have exponential vectors here, EU, tensor product EV, which means as a function of xy is a function of two variables. This is the coherent vector EU evaluated at x multiplied by EV evaluated at y. This correspondence, identification of Hilbert-Schmidt operators in L2 Rn with the Hilbert space L2 Rn tensor Rn, you make this correspondence and denote it by I. And note that this is scalar product preserving. But because this is scalar product preserving and these things span weakly the whole Hilbert space, this extends to a unitary isomorphism between this Hilbert space and this Hilbert space. So, this is an identification isomorphism between two Hilbert spaces. But you also note, because this is rank 1, it has trace. Now, you compute the Wigner transform of this operator, the Weyl-Wigner Fourier transform of this operator, namely you compute trace of EU EV bar WZ, the Weyl operator, which is nothing but, because you are computing trace, you take this part there. So, this is nothing but EV bar WZ EU. But you know how Weyl operator operates on these exponential vectors. It is EU plus Z multiplied by a scalar factor. So, you have an explicit formula for this. And if you do some algebra with this by using the definition of WZ, it turns out to be equal. And you also recall the definition of the exponential vector in L2Rn as I did in the last lecture, and then you simply compute. That is an interesting exercise. Then this becomes equal to the following expression: 2 pi to the power n over 2. So, that is an exercise for you. It is equal to E of some other, it splits into 2, E u dash at the point x multiplied by E v dash at the point y. It is a function of two variables, because now it is an element of this where z is equal to x plus iy. And the interesting thing is u dash v dash turns out to be minus of the identity in the first identity is of order n applied to uv. Sorry, this is not x but root 2x. This is some algebra here involved. This is root 2y. And because of this, sorry, that is also I think 1 over root 2 here. Right? So, because of this, the EU EV bar, the Fourier transform of this operator, this is of trace class. So, you can define this z is equal to this expression, and if you analyze this, what has happened is this EU dash EV dash that equal to this because of that, this function is nothing but the second quantization. Let me call this as this unitary as u. Second quantization of u. What is meant? What do you mean by second quantization? Simply gamma of any. It can be any L. It need not be L2 Rn. It can be L2 R2n, as it happens here because of the tensor product. Every one of them as exponential vectors. Gamma u applied to EV is nothing but E of u, the unitary applied to V. This gamma u is unitary. That is called the second quantization operator. Simply E of exponential of something becomes exponential of u applied to the entry there. That is second quantization. So, because of this, you have u dash v dash here, and therefore, it turns out to be first step. I start from EU EV bar, identify it as a function in L2 Rn, tensor Rn, L2 Rn, and then you apply from u from E of uv. You are now going to E u dash v dash. That means you have applied this unitary operator. So, it is gamma u, and then there is a scale change. Xy is changed to root 2x, root 2y, and you borrow one root 2 from here. So, there is a dilation transformation here. D root 2 and there is a 2 pi to the power. So, this 2 I have borrowed there. So, it now becomes pi to the power n over 2. This applied to EU EV bar. But you note that this is a Hilbert space isomorphism. Gamma u is unitary. This is dilation. Dilation means d theta applied to f evaluated at x. If it is in n dimension, this is f. Apply theta here x, and then here theta to the power n by 2. That is dilation by theta, and this is unitary. And d theta 1, d theta 2 is d theta 1, theta 2. So, all these three are unitaries. I, gamma u, this is unitary from one Hilbert space to another. This is unitary in L2 Rn, L2 of R2n. This is also L2 of Rn direct sum Rn, which is R2n. And this is EU is an element in Rn, EV is an element in Rn, and you are having tensor product, so you get a function here. So, all these are unitary, and therefore, this implies in particular a trace class operator is also a Hilbert-Schmidt operator. So, rho hat of z is equal to pi to the power n over 2 into unitary applied to rho. This one will extend to all trace class operators. In fact, all Hilbert-Schmidt operators it will extend. So, because of this, rho is nothing but pi to the power minus n over 2, and you have I inverse, that is from space of functions you go to the space of operators. So, you have I inverse, and gamma of u dagger, gamma u, gamma v is gamma uv, and then this dilation will become d of 1 over root 2 applied to rho hat inverse. D root 2 inverse is d 1 over root 2. So you have the required inversion formula, rho is equal to pi to the minus n over 2 multiplied by this. But this is only a scale change that comes because of our way of choosing the Weyl operators. This is only an identification. So this so-called Wigner-Weyl transform is nothing but second quantization of a unitary. Modulo identification and modulo a scale change, the Fourier transform is only simply the gamma of this unitary. And it is an interesting fact. We all know that the Fourier transform to the power 4 is identity in the usual L2 or n. If you take unitary Fourier transform, f to the power 4 is identity, f squared is minus identity. And what happens here in this case of Fourier transform in the space of Hilbert-Schmidt operators, all the eigenvalues of this are 24th roots of unity. So the Fourier transform here, you have gamma u to the power 24 equal to identity. So with this difference, the quantum Fourier inversion tells you essentially that the quantum Fourier transform is the second quantization of a unitary operator whose 24th power is identity. So that is an interesting point of analysis here. Now I come to the formal definition of a Gaussian state. Definition of a Gaussian state. I had already shown, introduced this formula Wz equal to e to the minus I root 2 into sigma xj pj minus yj qj. So if I take Wtz with this parameter, that is a one parameter unitary group, that will become e to the minus I root 2 into t into this sigma xj pj minus yj qj. So what is this particular self-adjoint operator has a distribution in the state rho. And so, what is its Fourier, what is its characteristic function? So, if I take a state rho, the characteristic function is trace rho. That is, I want the expectation of this trace rho multiplied by this e to the power minus I root 2 t into this linear combination of p's and the q's, and this is a self-adjoint operator. So rho is said to be Gaussian if and only if all these have Gaussian distributions. That means this must be trace rho e to the minus I this as a function of t, it is a characteristic function of a distribution of the real line, and therefore the fact that this is this will have a normal distribution if and only if it is of the form some e to the power it into some mean value depending on all these x and y minus t squared by 2 if sigma squared of xy. That is the normal characteristic function. And you see that this is analytic, so you can differentiate any number of times in t, and the standard formula for the moments of the distribution leads you ultimately to the fact that all linear combinations will be Gaussian if and only if this Wigner transform, the Wigner-Weyl Fourier transform or the quantum Fourier transform has the following structure, namely trace rho w t z, z is equal to x plus I y, that is ultimately of the form t I can drop, because txj is another new xj and tyj is another new yj. So, it is enough to write this trace rho wz is of the form, I still keep this e to the minus I root 2 into some linear function of x and y, L of L transpose x minus M transpose y I root 2 minus some x transpose y transpose some positive definite matrix S, real positive definite matrix X multiplied by x y. It should have this form, and this tells me that L is the mean value, this is the mean value of the position of the momentum vector, M is the mean value of the position vector. That means L is trace P rho, that is L, and similarly trace Q rho, that is equal to M. And because of this root 2 factor coming Wz, when you have, because of this root 2 factor coming in, the square of that root 2 and the half they cancel. So, because of that, S is the covariance matrix, S is the covariance matrix of the observables P, and then there is this minus Q, minus of Q. So, what we still call, by abuse of language, we still call it the covariance matrix of the Gaussian Gaussian state, covariance matrix of the Gaussian state. So, we make the formal definition. Rho is a Gaussian state. So, what is the final definition? Rho is a Gaussian state if such a formula obtains, namely Gaussian state, which I will denote by rho g, rho Gaussian, mean value for momentum, mean value for position, and covariance matrix S. I denote that state by S. If the transform rho hat z is equal to this expression, it is equal to this expression. Now the question arises, suppose I start with this Lm and an arbitrary positive definite matrix. What is the guarantee that there exists a state rho such that rho hat of that is equal to this? So, for that you should have that positivity property which I mentioned. Only if this, because if there exists a state, then we know rho hat satisfies the positivity condition, the Srinivas-Wolf positivity condition. And that gives you the first theorem here. That involves quite some algebra, and if anyone is interested, we can discuss it in my office room, or I can give a small tutorial where I can show you the full algebra if it is interesting for you. So now you have the following theorem. Namely, if you let fz be equal to e to the minus I root 2 into L transpose x minus M transpose y minus x transpose y transpose yes xy, where z is equal to x plus iy. There exists a state rho such that rho hat of z equal to fz if and only if the following matrix inequality holds: 2s minus ij greater than or equal to 0 with j equal to 0 minus I 0. This matrix inequality should be fulfilled. That is necessary and sufficient for a state rho to exist whose Fourier transform, quantum Fourier transform is equal to this expression, exponential of some linear form plus a quadratic form. So I won't bore you with all the algebra involved in the proof of this. But it is an interesting calculation. You can also read the proof of this, for example, in Holevo's book on quantum statistics. I have my own little proof which I can give you if you feel like seeing it. Now, you see, this means S is, for example, you read from this this is a matrix positivity. If you read the portion from this matrix, if you choose one xi and yi here, that will give you variance of pj, variance of pj multiplied by variance of qj greater than or equal to 1 over 4. This will give that inequality. So this is for states, this is the complete uncertainty principle. Complete uncertainty principle. This inequality is the complete uncertainty principle. For any quantum covariance matrix with the P's and the Q's. Right? Where did I keep? So this is an interesting inequality. The quantum uncertainty principle is sufficient to ensure that this comes from a state. And this has many interesting corollaries and this property. Suppose the first thing you may note is that if I take two Gaussian states, rho G L M S, and then take tensor, suppose this is in L2 of Rn and then this is in L2 of Rn dash. So you have L dash, M dash, S dash. Take the tensor product of two Gaussian states, that is also Gaussian. This in Rn and this in Rm, then is Gaussian. The main vector will be L direct sum L dash, M direct sum M dash, but S direct sum S dash you must arrange because all the P's I am putting in one bunch and all the Q's in another bunch. If you write P, P dash, Q, Q dash, you have to rearrange to interpret S direct sum S dash. So that you have to remember. So that is the first corollary of this formula for a Gaussian state. Then secondly, if I take the L belonging to the symplectic group, note that I introduced this definition 2nr, this is equal to all 2n by 2n real matrices such that L transpose J L equal to J, where J is that matrix which comes there, minus I 0 I 0, which also comes in the uncertainty principle. If you take this group, why is this group important? If you apply this L to P and Q, L is a 2n by 2n matrix. This gives you a new set of variables, P dash and Q dash. If this is CCR, this is also CCR. And every linear transformation which preserves CCR is from the symplectic group. So they form the internal symmetries of the linear symmetries of the CCR. They are also known as Bogoliubov symmetries. I like to Bogoliubov automorphisms of CCR. Automorphisms of CCR. I like to mention this name for a peculiar reason always. Namely, when I joined the Indian Statistical Institute in 1956, that was the silver jubilee year of the institute, there was a big celebration and Professor Bogoliubov came as a guest from the USSR Academy of Sciences. And that was my first year. And then of course he gave a lecture which I didn't understand, at that time I didn't understand anything. But words like statistical mechanics, quantum mechanics, etc. appeared in that lecture. So for the first time for me. So sometimes key phrases uttered somewhere can also start your research work, even though you may not know any theorems about them. And these Bogoliubov automorphisms can be implemented by the gamma L, which I mentioned yesterday. And if you apply gamma L inverse rho G L M and then the covariance matrix gamma L. You know, when you compute, you will compute the trace of this multiplied by WZ. This you will take, and so you will have gamma L WZ, gamma L inverse, that will change Z to LZ. So this is nothing but rho G, but this also will change. You can, it is an exercise for you to compute the change here, M dash, and this will become L transpose S L. So the covariance matrix will be changed, and this you should compare with the formula which I wrote down yesterday for the multivariate normal distribution. There it was the full linear group, and it is the exact analog of that, the quantum analog, only the linear group is replaced by the symplectic group. Right. And thirdly,
what is this little L and little M?
huh?
What is this little L and little M?
Oh, L is the mean value of P, M is the mean value of Q.
Okay.
Yeah, I mentioned. 3, if you W alpha inverse rho G W alpha, that is the Weyl operators, this is simply e to the power minus 2I imaginary part alpha Z multiplied by rho G, rest remains the same, rho G L M S. And if you look at this, the covariance matrix doesn't change, but the mean values will change because Z is X plus I Y, so you will get L will be changed to root 2 times root 2 L plus root 2 times the imaginary part, M will change to M plus root 2 times the real part of alpha. So it will only shift the mean. The Weyl operators conjugation shift the mean only, they don't touch the covariance operator, whereas gamma L changes the covariance operator in this way. Now, fourth property, which is also very interesting, because all these calculations are very useful if you want to do what is called information theory in quantum Gaussian channels, right? That is, many people have shown great interest in developing what are called quantum Gaussian channels, and I want to pose some small problems toward the end of the lecture on those ideas. So 4. Now suppose I take rho G, a general remark before going to the fourth property. You have, for a state rho, you consider the Fourier transform Z, and then you look at rho hat, say Z1, Z2, etc., Zm, then you put 0, 0, 0. Note that this is in Z belongs to Cm, and I put the last n minus m coordinate 0. Then what happens? This is some other rho 1 hat of Z1, Z2, etc., Zm, where what is the state rho 1? Rho 1 is nothing but this is this rho is a state in L2 Rn, right? Rho is a state in L2 Rn. But this is L2 of Rm tensor product L2 of Rn minus m. And rho is a state here. Now I can define the following state, namely I have rho here. This is the first Hilbert space and this is the second Hilbert space. You take the relative trace over the second Hilbert space. That gives you a state R1, that gives a state rho 1 in L2 of Rn. This is the marginal, the first marginal of rho, and similarly if you take out trace 1, you will get second marginal on the other. So if I put 0, 0, 0 here, then this is rho 1 hat of Z1 etc. Zn. So that is the definition of marginal state. So if you take trace 2 rho g trace 2 of rho g L m s. So if you put all the last n minus m coordinate 0, you will get rho g L1, L2, etc. Lm, then that is the first, and then m will be, oh, I have this, let me write here k, m, this is k, and this is n minus k, then this is L1, L2, etc. Lk, m1, m2, etc. mk, and then the matrix is cut off. Yes, but you cut off the P1, P2, etc. Pk and Q1, Q2, etc. Qk. So that shows the marginal of a Gaussian. So that is the fourth important property. Marginal of a Gaussian state is again Gaussian. Is again Gaussian. So all the classical statistical properties are valid here except for the change in the group. So you can combine both. For example, this gives you many important information, particularly relevant to quantum information theory. W alpha, gamma L, this is in Rn. And then you take rho g, say Rn equal to Rk direct sum L2 of Rn equal to L2 of Rk tensor product L2 of Rn minus k. You take rho g1 here and then you take rho g2 here. Both are Gaussian states, and then employ on the larger, these are in L2 of Rn, and then you make a dynamics W alpha gamma L and then put a conjugate, and then you take a trace of the second, trace over this. This is the first Hilbert space, this is second Hilbert space. So apply the dynamics and contract. That will give you, that will be again a Gaussian state. if you combine this. If you don't contract, it is reversible dynamics, and if you contract, it gives irreversible dynamics. Both are important for analysis of Gaussian states and the role both in physics as well as information theory. They are important operations, and that gives rise to some new questions also, for which we don't know the answer. Okay, but before doing all that, one must produce examples, actual examples of Gaussian states. So, fifth property, coherent states are Gaussian. Namely, if you take CU, and if you compute its Wigner transform, namely or quantum Fourier transform, this multiplied by WZ, this is nothing but CU WZ multiplied by CU, but this is normalized exponentials, so e to the power minus norm u squared over 2, again this will come, so it will be norm u square multiplied by EU, and if you make this operate on EU, then you will get EU plus Z multiplied by scalar e to the power minus half norm Z square minus Z U, right? That is how this will operate. This is E of U, scalar product U plus Z. So you have E to the power U plus Z. But you see this cancels out. So you have only, here you have UZ and there you have minus UZ. Sorry, here I have made a WZ applied to U minus half Z square minus ZU, and this is U plus UZ minus ZU. Okay, that is right. It is the imaginary part. E to the power twice imaginary part UZ minus half x square plus y square. But this is nothing but a linear form in Z, linear in x and y. This is linear in x and y, and this has covariance matrix identity multiplied by half, right? So it shows that this CU is rho G of, if U is written as U1 plus IU2, then this is U1, you can compute. So you fill the blanks here. I need not spend time on that. But the covariance matrix is half identity 0 0 identity. So coherent states are Gaussian. Right. The next example, I will give one more example and then write down the structure of the most general Gaussian state. The next example, first I will do when n is equal to 1, that is the simplest case. Now P and Q are non-commuting observables, but still you can consider a quadratic form in the non-commuting with the non-commuting observables, namely P square plus Q square. And here physicists have evolved a certain notation which is more convenient. You write A equal to Q plus IP by root 2 and A dagger is Q minus IP over root 2. For those who are interested in mathematical sophistication, this expression on the Schwarz space is closable, so it gives you a closed operator with a dense domain. Adjoint is also therefore of the same kind, and A and A dagger, they are adjoint to each other in the exponential domain or in what is called also in the domain of n particle vectors. I don't want to go into that. And A dagger obey the commutation relation A dagger equal to 1. It is like sometimes it is more convenient to work with the complex variables than real variables. So these are more convenient variables. Then if you write A dagger A, that gives you a self-adjoint operator, actually a genuine self-adjoint operator, which is half of P square plus Q square minus 1. So I consider this operator. This has some important properties. The exponential vector is that I am in dimension 1, n is equal to 1. So Ez can be written as a power series. It is actually z power n by root n factorial multiplied by some element in the Hilbert space L2 Rn, 0 to infinity. This is an orthonormal basis. This is actually the Hermite basis, right, in L2R. So Ez can be expressed in this way. The advantage of these exponential vectors is this is Ez, this is equal to z times Ez. So every z is an eigenvector, every z is an eigenvalue for A. So it is a good example. And A dagger A applied to n, this is simply a notation, a vector labeled by n, but this is an element in the Hilbert space, and that is Hermite polynomial multiplied by nth degree Hermite polynomial multiplied by e to the minus x squared over 4, suitably normalized to make the norm 1. That is a notation for that. So this is equal to n times n. So in view of this, A dagger A is called the number operator, because n is the number of particles, and that n number of particles has to be an observable, and that observable is A dagger A, and its eigenvalues are 0, 1, 2, etc. So this is number operator, and spectrum this is sulfur-joint, it is an observable, and the spectrum of A dagger A is 0, 1, 2, etc. Now I consider this e to the power minus s times A dagger A. This is a positive sulfur-joint operator. So e to the minus s A dagger A, it is a bounded operator, and you compute the trace of this on this orthonormal basis, and then prove for yourself trace of e to the minus s A dagger A. It is simply sigma e to the minus s n, the sum of the eigenvalues. And so this is 1 minus e to the minus s inverse. So you get a state. I get a state rho s, which is equal to 1 minus e to the minus s multiplied by e to the minus s A dagger A. And what is its Wigner transform? The Wigner-Weyl quantum Fourier transform, right? Namely, rho s hat evaluated z, which is equal to trace of rho s multiplied by wz. If you do it straight away, it is a little messy, but you use Sudarshan's theorem, then it simply reduces to evaluating a Gaussian integral. Because I can write here rho s, this is also trace of rho s wz cu du u equal to u1 plus iu2, u equal to u1 plus iu2, the real and imaginary part. Then this is du1 du2 divided by pi to the power n by 2, pi to the power n. But you know how wz operates on cu, because this is scalar times exponential vector, so you know the exact action. And it is an exercise, I don't want to go into the algebra, and then you have to integrate, right? You have to integrate out. Then it will come out as a product of two Gaussian integrals. And after doing all the calculations, that is a very, very nice exercise on this subject of harmonic oscillators. And this is equal to e to the power minus s by 2 cot hyperbolic s by 2 into z is here, so you will have modulus of x square plus y square. So that is a exercise with Gaussian integrals. That is e to the power minus some quadratic form plus some constant times the variable, where the constant can be complex. And that is why this cottage appears in the exercise in Gaussian integral. And also a very nice application of the over complete coherent basis, right? So this rho s, so rho s hat is equal to rho g 0, 0, half cot h s by 2 into identity 0, 0, identity. And you recall the old CU, which are also Gaussian, they all had covariance matrix half identity 0, 0, identity. Here the variance of position into variance of momentum is 1 over 4, but here it is 1 over 4 cot h is s by 2 square, and cot h s by 2 is greater than 1. Of course, this is meaningful only when s greater than 1, because I have e to the minus s a dagger a. Otherwise, you won't get a state. Right? You cannot go continuously make s go to 0 there. So you have this. These are the pure Gaussian states. Okay. And that is an example of a mixed Gaussian state. Now you can consider rho S1 tensor product rho S2 etc., and then tensor product some rho Sm, and then you can apply this Cu1 etc., remaining ones, and then you can conjugate by dynamics by the W alpha gamma L. Then you will get many Gaussian states, because taking tensor products and conjugation and contraction, they all leave the set of Gaussian states invariant. So you can get more Gaussian states. At this stage, a theorem from linear algebra comes. This is known as Williamson's normal form. Williamson's normal form. So I can state it as a theorem. Let S be any 2n by 2n positive definite real matrix. Then there exists L belonging to SP2NR and a diagonal positive matrix of order n, D equal to diag D1 greater than or equal to D2 greater than or equal to Dn. This is n by n such that S is equal to L transpose D D0 0 D multiplied by L. That is from linear algebra. Now, suppose S is a Gaussian covariance matrix. Let S let S be a Gaussian covariance matrix. Order 2n. Order 2n. Then S also can be written as L transpose D 0 0 D L with D greater than or equal to D equal to diagonal D1 D2 extra Dm. But you see, in order that this is eligible for Gaussianity, this must be 2 times S must be greater than or equal to 2S minus Ij greater than or equal to 0. But L transpose JL is J. That means this is equivalent to D0 0 D twice minus I times 0 minus I 0. This should be a positive matrix, which means each D1, D2, etc. should be greater than or equal to half. Right? The necessary and sufficient condition, because L transpose JL is J itself. So, by the way, in that theorem I have to mention that D is unique with that structure. D is unique. L can be different. So you choose the Williamson form with D1 greater than or equal to D2, etc., all greater than or equal to half. So let D1 greater than or equal to dk, then greater than half. This is the diagonal expression. This is n minus k times, and this is k. K eigenvalues, and n half has multiplicity n minus k. Now, because d1, d2, etc., dk are greater than half, each dj can be written as half of cot h Sj over 2. You can write like this. Sj positive. But if I want rho g 0 0 s, what will you do? Rho g 0 0 s. From this it is clear this is equal to gamma L inverse. Then you have rho S1 tensor product, rho Sk tensor product. The rest are half. For P you choose one, for Q you choose one. The D1, when they are written like that, they are like half of cot h Sj over 2 into 1 0 0 1. These are the covariance matrices associated I am writing, I am viewing Rn as R1 tends L2 R1, L2 R2, L2 R taken n copies. Write L2 Rn as L2 R L2 R n copies. In the first copy you put row S1, in the second copy you put row S2, kth copy row Sk. But now I consider the covariance matrix half 1 0 0 1, but that is nothing but the pure state psi 0 psi 0, which is also E0 E0. This is a Gaussian, this is a coherent state. So this is a Gaussian state with mean 0 and covariance matrix this. And this will come n minus k fold. That means this is a completely pure state. All this will be there. And what is the covariance matrix of this? That is precisely D0 0D, written in proper order. So this is gamma L inverse gamma L. That is precisely rho G00 S. And to get arbitrary means, you simply have to translate by the W alpha rho G 0 0 S and then W minus alpha or W alpha lambda. By choosing alpha properly, you can reach any arbitrary mean, because this won't touch the covariance matrix. So you will get rho G L L M S. So every Gaussian state can be expressed as a conjugation of products of the canonical state rho S, which I wrote down with the number operator, together with the so-called vacuum coherent state with some multiplicity, and conjugate by a unitary which implements the Bogoliubov automorphism L. So that is the structure of the most general Gaussian state. So I, of course, Professor Simon yesterday said I should lecture for 1.5 hours, but I think for me it is somewhat difficult. So I want to maybe one more talk, then I will finish what I have to say. And then this means I have only described what is already very well known in the theory of Gaussian state. Now only problems, new problems and questions arise.